In real aircraft production, perfect fit is basically a myth. Every part has tiny dimensional variations from machining, forming, or material behavior, even if it's made to strict specs. These small differences build up when you assemble thousands of parts together, so engineers plan for controlled imperfection rather than perfection. This pragmatic view helps aircraft go together reliably and also drives how we inspect, adjust, and compensate during assembly. Every manufactured part comes with tolerances, allowable variations from the ideal size, and when multiple parts stack together, those tolerance gaps add up, which can make assemblies misalign or produce gaps. Engineers calculate these tolerance stack-ups ahead of time to predict where problems might occur and either tighten tolerances on critical features or allow acceptable clearance so that assemblies still fit and function as intended. When you bring together big structures like a fuselage barrel or wing skin, fit-up becomes a major challenge because parts made in different facilities or even on different machines won't line up perfectly. Gravity, part deformation, and small distortions combine to make the actual assembly different from the CAD model. So fit-up often requires iterative positioning, measurement, and adjustment to bring everything into the right place before riveting or fastening. Shimming is the process of inserting thin spacer material between mating parts to fill gaps and align geometry when tolerance variations make direct fit impossible. Aerospace shims come in many forms: laminated shims, solid metal shims, and even liquid shim materials that cure in place. And they let engineers fine-tune assembly without remachining parts, preserving structural integrity and saving time on the build line. Shims do more than make things fit. How you use them affects how loads move through the structure. Properly placed shims help distribute loads evenly and reduce stress concentrations. But incorrect shimming can cause local overloads or change how parts deform under load, which over many flight cycles can accelerate fatigue or lead to premature cracking. That's why engineers carefully plan shim thickness and placement to keep load paths smooth and predictable. Fit-up decisions during manufacture don't just matter at build time. They affect maintenance later. A well-shimmied and aligned assembly will hold its shape better in service, make inspections easier, and reduce unexpected wear, whereas misalignments may lead to vibration, fretting, or corrosion that shows up years later. Maintenance teams often work with the original fit-up and shim data to track how variations evolve over time and plan corrective action before damage becomes serious.